Hello everyone and welcome to class number 3. We'll take our look at the syllabus calendar. If you don't know how to access this file on our Moodle site, go ahead and take a look at our video for class number 1. Today is class number 3. We're going to cover sections 2.2 through 2.5, types and properties of functions. So in front of you, you should have a hard copy of this document. It says class number 3 right here at the top. If you don't have a copy of this in front of you and you don't know how to find it on our Moodle page, again, watch the beginning of that video for class number 1. We begin on number 1. In this section, we talk about properties of general functions. The domain of a function is the set of all allowable inputs, and the range is the set of all outputs. Those are definitions of those two words. That's why those two words are underlined. Number 2, find the domain and range of these functions here. Okay, let's begin with part A. So we're looking for domain of this f of x equals square root of x minus 2. So domain is the set of x's that are allowed. So I'm just going to make up a number. For example, f of 7. If we plug 7 in here, we get the square root of 5. And the square root of 5 is some perfectly nice number. But if we were to try to plug, for example, f of negative 3 into this function, then we get the square root of negative 5, which is a problem. Square root of negative 5 is not a real number. It's an imaginary number, which is okay. It's an unfortunate use of the word imaginary, but we're not going to talk about imaginary numbers for a while here in this class. So when we talk about domain, we're trying to make sure that we get real numbers only in this class. So domain is a set of all x's that are okay. So the question is, what's the extreme? Let's see, x minus 2. I want to make sure that it's not negative. So in another sense, I want to make sure it's positive. If I make sure that that x minus 2 is positive, then when I take the square root, I'll be taking the square root of a positive number. One little detail, what about square root of 0? Is that okay? Is the square root of 0 defined? And the answer is yes, it's a perfectly good real number. The square root of 0 is 0. So then actually it's okay to make the stuff inside the radical equal 0. So we'll just make a general note here. Whenever you're finding the domain of a radical, domain of a square root, I should say, or any even root, let the stuff inside the radical, which is called the radicand, be greater than or equal to 0. That's always how we find the domain of a square root or fourth root or any even root. Let the radicand be greater than or equal to 0. And we solve for x, add 2 to both sides, and we get the domain. Domain is a set of all x's such that x is bigger than or equal to 2. If you prefer, we could use interval notation. Starting with x equals 2 and going forever means go to infinity. The square brackets means include 2 because x equals 2 is okay. The parentheses means don't include that number, and we never include infinity or minus infinity. Okay, for the range of this function, ranges are tougher to find, but maybe a real quick picture of the square root function would help us. So if I just wanted to graph the square root of x, then what would it look like? So pause the video for a moment and see if you can do a real rough sketch of the square root of x. So hopefully we got something like that. Starts there at the origin and then grows up kind of quick in the beginning and then slower and slower. It never levels off, so my picture is a little bit misleading. It goes up forever. And so if that function goes up forever, then what's the range, which is the set of all outputs of the function? So the range is all the numbers starting at wherever this function starts at the bottom, which is 0, and then the function goes up forever. It goes up to infinity, actually. So that means that the range of this function is the set of all y's starting at 0 and then going forever. It's all the y's that are bigger than or equal to 0. Or interval notation, start at 0, go forever. So that's the range of the square root of x. Well, what about that square root of x minus 2? Well, you have hopefully seen transformations before. That square root of the x minus 2 is just going to take the graph and it's going to shift it. It's going to take this graph, it's going to shift it 2 places to the right. And so it's going to go like that. And so the range is going to be the same. It's still going to start at 0 for y and go up forever. But you do see actually the domain popping up in here. We said the domain was all the x's bigger than or equal to 2. 2 is where this graph starts, and then it goes to the right forever. So that's the domain showing up. Part B, g of x equals 1 over x plus 5. So for domain, there's generally two things to watch out for. You want to take the square root of only non-negative numbers. That's what we saw first. And then the other big issue is to avoid dividing by one very bad number to divide by, and that's 0. So don't divide by 0. And so what that means is we're going to take x plus 5, and we're going to set it equal to 0. Even though we don't want to divide by 0, let's make it equal 0. And then whatever we get, we're going to throw out of the domain. So domain for a fraction involves setting the denominator equal to 0. And then exclude those numbers, whatever you get. Exclude them from the domain. Okay, so we solve this equation here for x. We get x equals -5. Is x equals -5 good or bad as far as this function is concerned? It is very bad. If you plug -5 in here for x, on the bottom you will get 0. That's a problem. So a -5 is excluded from the domain, and nothing else is excluded from the domain. So the domain is all the x's except for -5. So you can write it informally like that. I'll accept that. If you want to be more formal, you can use this thing called set builder notation. Set of all x such that x is not equal to -5. Interval notation is kind of clunky for this one, but we'll include it. Say or. Let's see, we can have any number except -5. So we're going to start from -infinity and go up to -5. And then we're going to start from -5 and go all the way to infinity. And we got to make sure we don't include -5 on either of these. So soft parentheses in both. That's our way of excluding -5 and only -5. And the fancy symbol for one set or the other set is this U, stands for the union of two sets. So that's the domain in 3 different forms. The range of this function is kind of challenging to find. But maybe if we have a good sense of what the picture is, then we can find the range. So thinking about the picture, this one is going to be a tougher picture for most of us. But if I gave you maybe a simpler function, y equals 1 over x, we have a sense of what the graph of y equals 1 over x looks like. So pause the video here and see if you happen to know and be able to figure out what the graph of y equals 1 over x looks like, and then come back when you're done. Okay, so if you got it, great. If not, well, that's okay too. I'm just going to draw it real quick. That's 1 over x. And then taking this graph and changing it to 1 over x plus 5, all it does is another shift. It shifts this graph left 5 units. So it's a new graph, but left 5 units. I'm not even going to draw it because the range is unaffected. So the range is a set of all the y values, all the outputs. So what different y values do we come up with? Well, let's see. We have all these y values up here, all the way up to infinity, and then all the way down to, well, it gets really close to 0. And then on the other side, we get all these negative y values going down to minus infinity and really close to 0 on the other side. In fact, the range is every number except a single number, and that number is 0. This is a really tough question. We're going to have an easier way to answer this. I'm just going to go ahead and put the range is tough, especially if you don't know the graph. But we're going to come back, and we'll have a technique to find the range of this function on the next page. So let's skip that one for now. Part C, domain and range of the function pictured. All right, this is much easier. So domain is all the x's. So let's see, looking at this picture, we can see that the graph starts here at -7 and ends over here at +7. So the domain is everything in between, including those two. We have to make it really clear to not include a point. We'd have to put something like an open circle there if I wanted to say don't include -7. And then the range is all the y values. Let's go ahead and put interval notation here just for practice. Parentheses or brackets. Included, so brackets on both. And then the range is a set of all the y values. So what's the lowest y value that we get? Well, it's down here at 0, and the highest y value is up here at 3. So the range is everything from 0 to 3. All the y's between 0 and 3, including both. Part D, the function that represents Bill Gates' net worth is a function of what year it is between 1950 and this year. Assume he had no money in 1950, he has $20 billion today, and his net worth maxed out 3 years ago at $30 billion. Okay, so let's think about domain and range. All right, domain is the inputs. Inputs are time. It's a function of the year between 1950 and this year. Okay, so that's the range. I'll go ahead and call it, I guess we can call it X, but maybe we'll call it T for time. It's all the T values between 1950, that's the first one, and then today. So I'm going to put this year. When you watch this video, it might be a different year, but I'll put that year right there. That's today. That's the end of the domain for right now. It's today. And then the range is a set of all the y values. This is net worth. So, so I guess y is an okay thing to put here, and we're going to have the range trapped between two numbers. So what's the biggest y value that we get? Well, let's see. The net worth maxed out 3 years ago at $30 billion. So over here, $30 billion. That's the biggest y value that he ever had. So that's the extreme end of the range. And then the minimum, well, it said he had no money in 1950. So presumably the problem is reaching for us to say 0. It's over there. I guess I'll not include the dollar symbols. We'll just have the numbers here. Now, it's actually not, there's not enough information in the problem to see if that's really the range. If he ended up owing money, then you could argue that the range should have some negative y values in it. I'll just leave it at 0 to 30, but I think we get the idea of this problem. Number 3, what does it mean for a function to be piecewise defined? And when would this come up? So piecewise defined just means that your graph has more than one piece, more than one rule. And it comes up whenever the rules change, whenever you don't have just one nice formula that captures everything there is to know about whatever you are looking at. So let's take a look at 4. It says graph the piecewise defined function f of x equals 2 minus x when x is less than or equal to 1, and 2x minus 1 when x is greater than 1. So let's see if you've got some experience. Hopefully you've seen these things before. But go ahead and pause the video here and come back after you have made your best effort to graph this function on these axes. Okay, hopefully you were able to make some progress. I'll begin with the top row. It says 2 minus x when x is less than or equal to 1. So I know that y equals 2 minus x is a line. And if I'm going to graph a line, I just need 2 points. So let's find 2 points that are on this line. One point that I'm definitely going to pick is the one where the rules change. So if I plug in x equals 1 into that top rule right there, 2 minus 1, we get 1. So this is the point, x is 1, and it turns out y is also 1. So I'm going to start there by plotting that point. And then we need one other point here. So one easy point is the y-intercept. The y-intercept is 2 in this case. I don't like to have my points for a line so close together, so I'm going to pick a point that's maybe a little bit further away. I'm going to kind of arbitrarily choose -5. Just got to make sure you're picking x's that are less than or equal to 1. So if I plug in -5 just to give me a point that's a little further away, so we got 2 minus -5 is 7. And so this is the point negative 5, 7. You probably picked a different point. But the nice thing about picking 2 points that are far away is that you can connect them with a straight edge or with a ruler. And little errors that you make connecting these 2 points don't really add up to much. But if you were to connect 2 points that were pretty close to each other, like trying to connect at that point, let's draw it in red here. If I asked you to draw a line that connects this point right here and that point right there, and the second point that I drew actually shouldn't have been there, but it should have been up a tiny bit higher, well, the two lines are quite dramatically different, right? And that line versus that line. But if I did the same kind of thing, I said, all right, connect this point and this point over here, but I made a mistake on that second point. It should have been right up there, which is about the same kind of error that I made with the first points. Well, these two lines aren't all that different. So that's why I like to pick my points far apart from each other when I'm drawing lines. Okay, so we'll connect the dots with our straight line. This line goes until x equals 1, so it ends right there on the far right. And then we'll connect the dots between, and then it goes forever that way, so we'll put an arrow. Not really mandatory for me to put those arrows. Okay, the next one, y equals 2x minus 1. Again, it is a line, so again, I need 2 points. So let's pick 1 point that's kind of far out here to the right. For example, let's pick x equals 5. So I'm going to pick 5 here. And if I plug 5 into the bottom rule, 2x minus 1. 2 times 5 minus 1, I get 9. So that's 0.59. And then we need one other point. And again, I like picking points that are far away from each other. But I also like picking points that are in the domain. I don't want to pick x equals negative 8 because negative 8 isn't part of that rule. I want to pick numbers that are bigger than 1. Well, it's not exactly true. I kind of want to know what's happening at x equals 1. Even though technically, if I plug x equals 1 in, I have to go here. I'm going to plug x equals 1 in, and I'm going to go here. And the way that I'm going to deal with the fact that this is a greater than and not a greater than or equal to is I'm going to put an open circle. Instead of a filled in circle or a filled in dot, I'm going to put an open dot. So let's plug in x equals 1 into the bottom rule, even though technically the bottom rule doesn't apply. So I'm going to write kind of a write some notation here. It's not universally accepted, but I think a lot of math folks would know what I meant when I said this. I'm going to plug in f of 1, but I'm going to put a little minus sign up there, and that's my way of saying, whoops, I'm going to put a little plus sign up there. And that's my way of saying, plug in x equals 1, but really follow the rule for numbers that are bigger than 1, more than 1. That's the plus sign. Okay, so plugging into the bottom rule, 2x minus 1, even though I'm not allowed to, we get 1. So this is the point 1, comma 1. So 1, comma 1 is, well, happens to be already there. So I was going to put an open circle, like if the point were at 1, 5, I would put an open circle there. At 1, negative 7, I'd put an open circle there, and then I'd connect the dots to the point that really exists. But you can't put an open circle because that would indicate the point isn't there. And this point happens to be there. So that blue right there, I'm going to put a purple dot right above it just so we can see it. But really, blue and purple are exactly in the same spot. And then we'll connect the two purple dots. And this one goes forever this way. Now, it is possible to type in this function right here, a piecewise function, onto your graphing calculator. It's kind of a pain. I'm going to show it to you. If you're not super interested in this, you can skip ahead. But here's how we do it on the graphing calculator. So the first rule is 2 minus x. It doesn't need parentheses, but we need to put them in here. Then we're going to type in other parentheses, this inequality, x less than or equal to 1. X less than or equal to is inside of this test menu. It's yellow. Second math. Less than or equal to is there, number 6. Less than or equal to 1. Close the parentheses. That's the first part. Then we're going to put something that doesn't appear anywhere in here, and that's a plus sign. And then I'm going to type in the second part in 2 different sets of parentheses, just like the first part. 2x minus 1. Close parentheses, open parentheses, x greater than 1. Greater than is in the test menu. That's number 3. Okay, and if I want to get this window from -10 to 10 on both, that's the standard window, that's a zoom 6. That's oftentimes a good way to start when you're drawing a graph. And we can see just what we drew here. When you're ready, move on to the next page. Number 5, what is the composition of two functions? If f of x equals x plus 3 squared and g of x equals 1 over x plus 5, find part A, f of g of 2, and then part B, g of f of x. So hopefully you've seen composition of functions before. If you have, pause the video here, fill in one or both of the answers to these problems, and then come back. Otherwise, you can just wait a few moments and we'll do it together. Okay, so the key idea here is work from the inside to the outside, so inside out. So I'm going to copy the f, and then I'm going to find g of 2. So g of 2, g is that second function over there, so we're plugging 2 for the x. And then we're just going to calculate what number is in the parentheses is 1/7. And now it's more straightforward. We just have to plug 1/7 in to the f function. So we go 1/7 plus 3 squared. And now there's just a little bit of arithmetic to do here. So we'll make this one improper fraction. So we get 22/7. That's squared. I think that 22 squared is 484. 49 goes on the bottom. Not 100% on that one, so let's double check. So 22 squared. Okay, and then part B says g of f of x. So same idea, work from the inside out. So we'll copy the g, and in the parentheses we do f of x. Well, we just copy. F of x is x plus 3 squared. So that goes right there. And here's the toughest part for a lot of students, is we're now going to take the g function and we're going to plug in. So what are we going to plug in? Well, how did we find g of 2 before? Well, we saw that there was a 2 in the parentheses, and we just put a 2 right there for the x. So whatever's in the parentheses, you just put right down there for the x. So that's what we're going to do here. What we see in the parentheses now is x plus 3 squared. That's inside of the g function. So right up here where I see this x, I'm going to put x plus 3 squared. So copying the g function, it says 1 over x plus 5. I'm just going to leave a blank for the x. Instead of the x, we put what's in the parentheses, x plus 3 squared. That's the x. And that's it. We can clean this up a little bit, but the hard part is done. 1 over, let's see, x plus 3 squared, x squared plus 9 plus 5. That's 1 over x squared plus 14. Is that right? No, it's not right. I'm hoping you were yelling at the computer screen right there. It's one of my favorite mistakes to hate when students do, so don't do that. X plus 3 squared. Maybe if it helps you write it twice. And that should hopefully jog your memory that you need to do some double distributive or FOIL or lobster claw, if that makes sense to any of you guys. So FOIL, and we get x squared plus 6x plus 9, and then the plus 5 is just hanging out. 1 over x squared plus 6x plus 14. Number 6, when is a function invertible? That is, how can we tell if a function has an inverse? Okay, so in your reading, or hopefully you've seen this in some prior math class, in order for a function to have an inverse, function must pass a test, a horizontal line test. Function has to pass the horizontal line test. That is to say, when you draw the function, for any horizontal line that you draw on top of that function, there better be one and only one place, or at most one place, where the horizontal line hits the graph. So let's go back to the first page of our notes here. And there's a graph of half an ellipse type thing there. And then there's another graph of a couple of lines down here. And I'm going to draw one random graph down here real quick. So suppose that the graph that I draw is something like that. So horizontal line test says you draw every horizontal line you can think of, and if any horizontal line hits the graph more than once, then the function does not have an inverse. I'll say it again. This is in your book. If any horizontal line hits the graph more than once, then the function does not have an inverse. So this function right here has an inverse, because no matter what horizontal line I draw, it's only going to hit the graph once, never more than once. Contrast that with this picture of the piecewise function at the top. Okay, these horizontal lines are fine, because they never hit the graph. That's okay. Just can't hit the graph more than once. This horizontal line is also fine. It hits the graph just once. But move up a tiny bit, and we get to a horizontal line that hits the graph twice. That's a problem. It means this function that's pictured does not have an inverse. Same kind of thing if we look at the question up above, the ellipse question. Can you draw a horizontal line that hits the graph more than once? You bet. That one. It hits here. It hits here. It fails the horizontal line test. It does not have an inverse. Okay, so I think where do we need to be? So let's go right here. All right, so let's go to number 7. It says decide if the functions below have an inverse. If they do, find a formula for the inverse. When we're done, we'll relate our answer to part B to our discussion of the range of the function in part B. Okay, so we'll start with part A. Does this function right here have an inverse? Well, I'm going to start by drawing a picture. You don't need to start with a picture, but I'm just going to start there. Okay, x plus 3 squared. Pause the video. See if you can draw a rough sketch of that function real quick, and then come back. Okay, hopefully I've drawn a parabola. Standard parabola has the vertex at the origin. That plus 3 just moves the graph left 1, 2, 3. So there's the graph. And what do we think about this function and the horizontal line test? Well, you can draw a horizontal line that hits the function in more than one place. This function fails the horizontal line test. F does not have an inverse. Or at least I should say the inverse of f is not a function. Okay, what if you didn't have the picture in front of you? What if you just wanted to follow a procedure and then see what happens? Is there something that's going to tip you off in an algebraic procedure to let you know that this function has no inverse? And the answer is yes. So here's the procedure. You've hopefully seen it before. Instead of f of x, we'll just call it y. Next step in the procedure is to interchange the x's and the y's. Swap them. And then the hard part of this procedure is to solve for y. So we're going to try to solve this equation for y. So first we'll take the square root of both sides. I'll put it up here. So we go square root of x equals y plus 3. Then subtract 3 from both sides. Square root of x minus 3 equals y. And then last thing, instead of the y, we're just going to put the symbol for the inverse function. That symbol is f to the minus 1. That's the symbol for f inverse of x. Okay, well, it seems like we've got kind of a contradiction here, because we said on the one hand f has no inverse, but it sure feels like if I did my process right, that right there is the inverse of f. We found it. So here's the mistake that I made. I took the square root of both sides of an equation, and I forgot to do something that's very easy to forget to do, and that's to put in plus or minus. So right here, I should have put plus or minus, I should have put plus or minus, and I should have put plus or minus. And so now if I just gave you this formula, let's say I just said, hey guys, h of x is this function I'm thinking of, and it's plus or minus the square root of x minus 3, you should say, wait a minute, that's not a function. Because you can pick a value of x and have two different values of y that pop out. For example, if you pick x equals 1, how much is h of 1? Well, it's plus or minus the square root of 1 minus 3. It's two different things. Plus or minus 1 minus 3. Some of you could say legitimately that, oh, the answer here is -2, and others could legitimately say the answer is -4. And that's a single input with two different outputs. So not a function. Okay, what if we try to follow this process for b? B is a function that we saw earlier. It's on the previous page. I can't draw it. I mean, we drew it on the previous page, but it's a lot tougher, and it's not really one that I expect you just have in your toolkit of functions. So let's see if we can just follow the algebraic procedure and see if we can find the inverse function for part B. Okay, so let's do that here. Instead of g, we're going to call it y. Then we're going to interchange the x and the y. And the goal is to solve for y. Easier said than done. Take a moment, pause the video right here, see if you can solve for y, and then come back when you're done. Okay, so hopefully we multiplied both sides by y plus 5. It's fine to distribute there, but it's not mandatory. In fact, it's probably easier to move that x over. Don't distribute it, just divide both sides by x. And then still trying to solve for y, so we go y equals 1 over x minus 5. And then finally, instead of y, we'll call it g inverse of x. So that right there is the formula for g inverse. And it is a function. We never got like a plus or minus. You pick any x you want, except for 1, and you can plug in, and you will get one and only one output. Single input gives you a single output. So that's a function, and that right there is g inverse. Okay, and then I mentioned up here in the directions, it says we're going to look at part B, and we're going to think about the range of part B. So here's a question I'm going to throw in here. What is the domain of G inverse? Domain of G inverse. So remember, domain, there are generally two things you're looking for. You want to make sure that you avoid taking the square root of what kind of a number? Negative. And you want to avoid dividing by what number? 0. So we just have to make sure there's no square roots, so we just have to make sure that we don't divide by 0. So the only bad number would be involving division by 0. So the domain here is all the x's that aren't 0. Okay, easy enough. But here's the nice part of getting that answer. The very first thing that we did here was swap the x and the y. Swap the x and the y right there. So when we say the domain of G inverse is all the x is not 0, well, we can think about what that has to do with G. This is G inverse. But what does this thing have to do with G? Well, the x's and the y's got swapped. So the domain of G inverse should actually be the range of G. I'll write that down. Domain of G inverse is equal to the range of G. How come? Because when you're going to G inverse, you are swapping the x and the y. And the domain of G inverse is what we just wrote. We said that the domain of G inverse is all the x's not 0. So that must be the range of G, except it's the range, and it's a y thing, and we swap the x and the y. So instead of saying the domain is x not 0, we say the range is all the y's, except for 0. So this is how you can find the range of a function. If it's got an inverse, and if you can find the inverse, then maybe find the domain of that inverse function, and whatever you get will be the range of the original. Some pretty heavy concepts, but let's see if what we just boxed there agrees with what we wrote on the previous page. The range here is all the y's that aren't 0. This is the function 1 over x plus 5. Okay, here's the function 1 over x plus 5. We just discovered the range is everything except for y equals 0. Well, what did we see when we drew this more complicated function? We drew it right here. Well, we just drew 1 over x, but 1 over x plus 5 just shifts it to the left. That's fine. well, what's the range of this function? Well, we said before, you get all these positive y's going forever. You get very close to, but never equal to 0 for y. Then you get all these negative y's going forever. And then you get very close to, but never equal to 0 from the negative side. So what's the range of this function? It's every single y value except for 0. So it agrees with what our picture showed from before. Okay, moving on to number 8. Suppose B equals f of t gives the balance in a savings account t years after the account is opened. Write an equation that represents the inverse of this function. What does this inverse function tell you? What are we assuming when we say that the inverse of this function exists? Okay, so first we can write the equation. So the equation just involves, putting the, well, I'll write this equation here. I'll leave a little space. And what we're going to do is we're going to essentially take f inverse of both sides. Kind of like add 7 to both sides. That's legitimate to do. It's also legitimate to take the inverse of both sides. And when you do that, good things happen. F inverse of f cancels, and you're just left with t. So the formula that we have here is t equals f inverse of b. So that's a formula for the inverse function. So let's think about what the original function tells you, and then we'll think about what this inverse function tells you. So the original function has an input of t and an output of b. So let's just make a little chart down here to help us keep track of what's what for these two functions. So the first function we'll say is the original, and then the other function we'll say is the inverse. And then we've got input and output for both. Okay, so for original function, what is the input? What letter is the input? So the input letter is t, and the output is b. That's for the original. And then when we go to the, did I do that wrong? I did. Output is b. And then when we go to the inverse, well, the inverse function swaps the x and the y. So I feel like we should just swap the t and the b, but let's make sure. Is that what this says? Here's the inverse function. There's the input letter, it's b. There's the output letter, is t. So indeed, they do swap. Input is b, output is t. So let's see if we can write a sentence for the original function, and then we'll write a sentence for the inverse function. So for the original, given input, the given was the t, and t was measuring time. It's the balance in a savings account t years after the account is opened. So given a certain amount of time after the account is open, the output of the function is the balance in the account. So maybe after 1 year, you got $1,000 in there. After 2 years, maybe it's $1,200. After 10 years, maybe you're at $8,000. So given some time, this function spits out the balance in the account. But now we're going to swap the roles of the two pieces. So for the inverse function, we're not given time anymore, but we're given the balance in the account. And then the output is the time. Time it takes to reach that balance. So go in the other direction. Maybe you are given a balance of, say, $8,000. And you say, well, I want to know when will I have $8,000 in that account? And this inverse function will tell you that. You plug in $8,000 as the input of the inverse function, and the output is how long it's going to take you to get there. So maybe to get to $8,000, it will take 10 years. To get to $1,200, it will take 2 years. And then the last part of this question said, what are we assuming when we say the inverse exists? Well, we're assuming that that this function has an inverse. And is that reasonable to assume? Well, it may or it may not. If you just put money into the account and you let it grow because of interest, and you never take money out, then the function will be increasing all the time. So this is the original function. Time is here, balance is here. Maybe originally you put $1,000 into the account and you make some deposits, so it grows, and you make some deposits and it grows. Never take anything out. So the horizontal line test here is passed because it's always increasing. So this function has an inverse, no problem. But as soon as you take some money out, well, you got problems. So maybe you put your 1,000 in and you let it grow, but then you need some money, so the function jumps down to here because you take some money out, and then maybe it's going to grow again. This is not a function. This thing doesn't have an inverse, which kind of makes sense because here, if I were to say, well, how long does it take me to get to, say, $1,200? Well, that function no longer has a unique answer. There's 2 different times when you get to $1,200. So the inverse isn't a function. Okay, next page, number 9, concavity. For x bigger than 0, f of x equals x squared, and g of x equals square root of x are both increasing, but there's a difference in how they are increasing. Graph these 2 functions below. Pause the video, draw your best sketches. X squared can be on the left graph and square root of x on the right graph, and then come back when you're done. All right, hopefully these 2 functions are in your toolkit and you can draw them without too much effort. So I've plotted a few points on each, a few nice points on each. And we get these 2 functions. So if we look only for the x's bigger than 0, so we'll highlight here in green, so starting here and going this way, starting here and going this way, what's happening to the y values? Well, on this function, as you run to the right, what's happening to the y values? They're getting bigger. On the other function, as you run to the right, what's happening to the y values? They're getting bigger. So indeed, both functions are increasing because as you walk to the right, the y values are increasing. But they're increasing in a different way, and we're going to really be clear about how to measure that different way. First, let's read the next part. We can make a similar comparison between the graphs of the height of a ball dropped from a building and the height of a landing plane. Which graph is which? Pause the video, figure out which one is the ball and which one is the plane, and come back. Okay, for the sake of the folks on the plane, I hope we chose correctly. So the first one over here indicates something falling quicker and quicker and quicker until it hits the ground. We hope that is the ball. And the other one is still falling. The altitude is getting smaller, but it's falling slower and slower. So hopefully we'll make a nice safe touchdown on the runway. Number 10, this difference is concavity. So they're both decreasing, but they're decreasing differently. Concave up means the curve bends upward as we move from left to right, which means the rate of change is increasing. Concave down means the curve bends downward as we move from left to right, which means that the rate of change is decreasing. Let's identify the concavity of each of the 4 functions from question 9. Okay, concave up just means the curve is bending upward as we move from left to right. So let's come up here. In this picture, first picture, as you move left to right, the curve is bending. I would argue that this curve is bending upward. So it feels like that one right there is concave up. But in the other picture, as we go left to right, this curve is bending, but it is bending downward. It's not going down per se, but instead of being a straight line, it is bending away from that line and curving downward. It is going up, but it is going up slower and slower. So this one right here is concave down. So these 2 graphs right here, one is concave up and one is concave down. The one that's concave up is the one that is bending upward as you go from left to right. So pause the video, see if you can identify which graph is concave up, bending upward from left to right, and which graph is concave down, bending downward from left to right, and come back when you're done. Okay, hopefully we see that this first graph is concave down. It is bending downward from left to right, and this graph is bending upward. So it is concave up. Okay, number 12. Here's the graph of f of x equals 6x minus 1/2 x cubed. It's this picture here on the right. Identify the intervals of increase, decrease, as well as the intervals of concavity. Note that we always write our intervals in terms of x. Okay, so let's just start making some notation over here. So we want to know where the function's increasing, where it's decreasing, where it's concave up, and finally where it's concave down. Okay, so let's handle the increasing part first. So as as this graph, as you walk along this graph from left to right, where are you increasing? So maybe pause the video here and answer the increasing and the decreasing parts and come back when you're done. Okay, so hopefully we found that in the beginning here, the graph is going down, decreasing until we get to there, and then it's increasing until we get to there, and then it's decreasing the rest of the way. So if we agree with that, then it's just a matter of figuring out how to write it. So it starts off by decreasing. That means from minus infinity, if we assume it goes forever to the left, until it gets to the bottom number there, which is at -2. Okay, and we never include infinity or minus infinity, so that's parentheses. I'm probably going to not include -2. I'm going to say it's not decreasing at -2. It's just kind of flat. It's paused there for a moment. But if you include -2, I have no problems with that. Okay, then it starts to increase from -2 until we get to that top point, +2. And again, I'm going to exclude both of them, but you could include both of them. And then it's decreasing again, starting at 2 and going forever. And then we'll put our fancy union symbol in between. And I just want to point out that when we talk about increasing, decreasing, we're only thinking about x's. So when x is -2 and when x is +2, all the numbers in between is where the graph is increasing. We don't make any mention of -8. We don't say it's increasing from -8 until +8. We don't talk about the y values at all. These intervals are always in terms of x. Okay, next thing is to think about concave up and concave down. So see if you can pause the video and write down the intervals there and come back when you're done. Okay, let's see what we've got. So this function in the beginning, it is here, is this thing here, as we walk left to right, is that bending upward or downward? So I would argue that this is bending upward, still bending upward, continuing to bend upward, but then at some point we start to bend downward, and it's not up here, it happens earlier. We are already starting to bend downward down here. And it feels to me, this is just an estimate, like the change happens right around there. As you are to the left of that, you get things that are bending upward until you get there. And then to the right, things that bend downward forever. So I think that to the left of 0, we are concave up out there. And to the right of 0, we are concave down. And let's see if that agrees with what we wrote up above when we categorized these 4 graphs. Let's find the 2 that are concave up. So top left is concave up. Bottom right is concave up. So look at the top left graph that looks like an upwards parabola. It is an upwards parabola. So which part of this thing looks like an upwards parabola? Well, it's all of this. Looks like an upwards parabola until we get to about here. And then it changes and it looks like a downwards parabola. And that's it. So we're right. Concave up is the until 0 and then concave down after that. So concave up, all the x's, only x's, until 0. So that means it's forever to the left until we get to 0. Never include the infinities. I'm not going to include 0, but you're welcome to. And then concave down is starting at 0 and then going forever to the right. When you're ready, next page. 13. What does a function that's not increasing or decreasing look like? So something that's not increasing or decreasing is a constant function, which is a horizontal line. How about a function that's not concave up or concave down? That is to say, a function that's not bending. Well, any straight line will do. It can be an uphill line or a downhill line, or it could be horizontal, but a line has no concavity. 14, sometimes it's hard to locate changes of concavity or changes from increasing to decreasing or vice versa. Calculus will prove very helpful here. Okay, next piece here is the significance of concavity. This is our first activity, and I want to talk about it, but let's come back to it. Let's just jump to the learning objectives, and for the last time in the video, we'll talk and make sure that everybody's very clear on what's due and when it's due, and then we'll go back up to the activity. Okay, learning objectives after class 3. We just finished class 3. You can see class 3 is the row that's highlighted here on our spreadsheet. So on Wiley Plus, the homework assignment you are going to do is called homework 3. That 3 matches with this 3 right here. It is due 1 week after it is assigned. It is assigned, well, whatever date you have there in that highlighted row, that's when the homework is assigned. Add 1 week to that date, go to midnight 1 week later, and that's when the homework is due on Wiley Plus. After attending class, you should be able to, and working very hard on all of this math, should be able to do these different things. So use that as a checklist. Your preparation, reading ahead, involves reading sections 4.2 and 4.3 in the book. After you do that, you're going to answer these questions right here based on that reading ahead that you did. Again, you're going to email your answers to these questions of the day to me, and please, 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 in the subject line, put QOTD and the class number and your last name, something like that. Okay, and then finally down here, other things to do. Continue working on project 1. You can see here that project 1 is due right there. Project 1 is collected in this row, so class number 5. That's when project 1 is due, so you should be working on that, continuing to work on that. And then we have our first quiz. Our quiz takes place next class, and you're going to see the calendar and the syllabus for more information. You can write anything you want on a 3x5 index card and use it on the quiz. So any formulas, any definitions, any practice problems that you want to have access to, you can just write them on the front and back of a 3x5 card and use it on the quiz. We haven't had any quizzes yet, so let's look at the calendar. It says right here, quiz number 1 is happening next class. We just finished class 3. Next class is class 4. This quiz is on classes 1, 2, and 3. That's this information here, all this stuff. These sections in the book, these class notes that we've already gone through. So the quiz is happening next class. So the quiz may or may not count. This semester that I'm doing this class, the quizzes don't count. You can just go download them on Moodle and then upload them at your leisure, and I will grade them and give you feedback, but I won't record your grades. That's only the policy for this semester. So just be very careful as you read the syllabus about the policy on quizzes. And that is the set of learning objectives. So let's go back here now to page 4. And we'll go to this thing called the significance of concavity. So this is our first activity. And I'm hoping that when I've said pause the video and then come back when you're done, you have done so. And we've had lots of little problems for you to do on your own and then come back. So the activities are generally bigger problems, deeper problems, and more numerous problems. And I'm not going to make a video. I'm not just going to do them right here as part of this video because I want to really make sure that you pause the video. You don't just wait for me to do the problems and then just write down the notes. I think if you do that, you will be shortchanging yourself. So I strongly encourage you to work on the activities. You can work on them together if you can find people to partner up with. And really plan on spending, like a good 20 minutes, maybe half an hour, maybe more, depending on the activity, working through it. It's really not supposed to be like a 2-minute thing like some of the other places where I've said pause the video. So you're going to work through the activity. The directions are there. There's a bunch of problems. For almost all the activities, I have answers. I don't have an answer key for this one, but I will tell you that I am going to make a video of me going through these problems in the activity. And so you will have an opportunity to watch that video. It'll be up on YouTube. Here is the title that you're going to search for: 108 Class 3 Activity. No spaces in there. And if there's an activity in Class 4, you just change that number right there, and that's how you'll find the videos of me going through the activities. But I strongly encourage you not to just go there right now, but rather take your time, work through this activity, and only when you want to see what I had to say about it, do you go and take a look. Also, where I download or upload the PDF, this is the material for the first test. Right here is a PDF of the filled in class notes. It will, of course, have these things filled in as well. So you will have answers to these problems in color once I've made the video, and I'll post them as a PDF right there.